Okay, so in continuation to what we saw in our regular classes, we are going to talk more details about process states. Understand here, we are not starting with theory. We are going to observe Ubuntu like a detective. Now, suppose if I ask you a question, let us say if you execute dot slash a dot out, what do you think? What happens? Yes, what happens? Can anyone address that? Okay, let me start with something simple. Think about say Pune during Holi. Imagine you are on FC Road or probably JM Road, like on the Ranga Panchami day, like say today. You will experience music is everywhere. People throwing colors, water guns are there, huge, or you can say loud dhol is there. Now suppose only one narrow lane is open and hundreds of peoples want to pass through it. What will happen? There would be a chaos. Correct. So now imagine a police officer standing there, having a whistle in hand. He stops one group, allows another, controls the flow. Correct. And the traffic police officer is your scheduler. Okay. Now, how exactly he would be picking the things? Let us try to understand first through the process states. So the question that I ask you, like if you execute or you say double click a program, like for example, a dot out, what happens? It executes or it runs. But running is not just a single condition. Inside Ubuntu, your program keeps changing its condition continuously. It moves between different states. Today, we will understand that journey and will not just work with respect to the bookish diagram that you might have seen rather, but we'll try to prove it using a working C program. So let us say if I write man ps, you will realize this is the output of ps command, okay, which is shown to us. And if I go say below, okay, and sorry, try to say reach to the states where the details are given, symbols. Okay, I'm going below, go downside. Okay, let us try to understand the symbols that are shown there with respect to the process states. Okay, okay. So these are the process states for us. You can say process state codes used in Linux. Now we understood two important terminologies, a program and process. Like when I say a C code or a file containing C program, is it a process? Actually, no, because it is just a program which is static file stored on the disk. But when we compile and execute that, then that becomes a process. And definition, one can say naturally like this. A process is a program in execution along with its memory, register, stack, heap, and state information. Like in Ubuntu, everything running, like when we write PS, everything running is a process. It could be your terminal, it could be your browser, it could be your VS Code app, or even different system services. Now, let us say if I write PS, these all these all that are shown to us, like two of them are shown to us currently are the processes which are alive on our system. And when I write PS-A, then it shows me all processes on that server, okay, which are now alive. Okay, these are the programs running as a process. Now, when we talked about the process states, the states codes, say for example, if I go and check it, There are different codes given like D, I, R, S, T, small t, W, X, Z. Now, these are the states codes. But generally, like if I talk about, if you see the classical process state diagram in given in either of the book, which I understand you definitely must have seen, whether you must have seen something like new, ready, running, waiting, terminated, and so on. So in general, one can say that there are importantly five main states: new, ready, running, waiting or blocked, and terminated. Now, like if I ask you like draw a process state diagram, you definitely would be drawing that diagram which you must have seen. But the way that the diagram is shown, say let me open say for a while the PDF that we were using inside the class. Correct. So let me go below and let me open this one. So this is the kind of one can say diagram that you will see given in book. Now there are some arrows given and so on. So this is not just kind of a diagram that you might be asked to draw. This is exactly what your Ubuntu kernel implements internally. Now we will try to observe each of these states practically. Like this is in general process state diagram given. Like these are the states. So you shift from new to ready, ready to running, running to terminated, running to waiting, waiting to ready, running to ready, and so on. Similarly, like if I see with respect to say a varied one, like a modified one can see this one too, like all internal states. But if you talk about just Ubuntu or Linux perspective, so let me show this diagram to you. It looks like something like this. So this diagram is captured from Maurice Bach book, The Design of Unix Operating System. Now let us try to create this kind of scenario, not as a diagram perspective, but programming perspective. Can we see these details of the process states? Okay, now how to do so? So like let us try to see the same thing through different set of programs. So like let me ask again another question. Like when does a process gets created? So we know when we execute a program. So what happens at Linux? We already saw that process creation happens using fork. Correct. Then fork, I assume you must have seen that exact scenarios which got created. Correct. In front of you, like through the different set of videos. So when you write dot slash a dot out internally, the system calls like fork, exec are called, and one can definitely see them. Like if I say, if I write say strace dot slash a dot out, okay, you will realize like different system calls are used internally by the system. Okay, starting with say exec CVE because exec CV before exec CVE it was fork and fork through exec CVE replaced that bash by a dot out. Now, if I try to really see what is the status of this particular file, rather which is running, if I write say ps-ejh, the program that I wrote, a dot out was created for it, and then if I try to see this, there is a dot out because it is running now. It is waiting for some input, my input, and if I try to write say ps-eux grep a dot out. Let us try to see what is shown with respect to a dot out. So this is where our a dot out is. You will realize it is having something with S plus. This is shown for because S trace was fired by us. Correct. Then a dot out. This is the one that I'm really exactly talking about. Correct. Now, what exactly is happening here when your exec executed or exec CV executed this a dot out? The process got created, the image was replaced, the program image was replaced by the new image. Okay. Memory allocation was done, PID was given, PCB was created, and because of that PCB only one could find out these more details about that particular process. But now how exactly I can realize, like what exactly do I mean by this S? What exactly do I mean by others of them? So let us do it via a simple set of codes. Okay, let us understand that. Though I executed the program which was created earlier, let us do this by writing simple code. Let me tell you one thing. Ready process states or new doesn't mean running. Okay, I am fully prepared, just awaiting for CPU. Like for example, if I go to this diagram, it's a state diagram, you can see this one. Correct. So it says user running, but what happens, like, or if I write about create, 7 fork is given. So is it really executing when it is shifting from the states? Even if I go back to, like, say, for example, with earlier diagram, when it says new, when it becomes ready. So am I really executing new ready? Because recall the example that I talked about in the class, like while I am entering in the room, I'm allowed to execute. Then I'm ready to execute. And then I'm executing. These are the three different things. So I'm fully prepared, but just waiting for the CPU to be allocated. So in Ubuntu, there may be hundreds of ready processes, but only one process per CPU core, depending upon number of cores that you have in your machine, can run at a time. And let us demonstrate this part, like how exactly it happens. So let me write a simple C code here. Let me write, say, Emacs CPU state dot C. Yeah, let the browser open. Yeah. Hash include stdio.h. Okay, no, I'm not using any of the process, what can I say, process calls or system calls. Just I'm simply writing a code like while one, then return 0. Okay, let us assume that this code works. Let us save this. Let us compile this code. So I will write GCC -m32 CPU state.c, and let me create executable with same name, CPU state, with assumption that there was no error. One can see. Now let me open or execute this code. Now it continued the execution. Let me go back to some another terminal. Correct. Now we know. Let us fire the command top. If you recall, I talked about that top command that day. Okay. Or let me show you what exactly top is. So top is used to display Linux processes. So like we know that our program got executed on another terminal CPU state. Fine. Now if I write top here, this is our code. Okay, let me increase this. This is our code. And you can see the state code as R. Can you see this R? Please mark thumb in the chat window if you can see this. I want you to, or maybe add emoji there, so as I can see what exactly is shown over there. Can you see R there for CPU state? Or you can unmute yourself and say yes. Are you there? So, like what exactly we did now, right now? We tried finding out that our process is running in the CPU. Okay, you can exactly see like 100% CPU or something, sometimes 99.3% of CPU is used. Now let me open one more terminal. Correct. And let me execute the same code from here. Dot slash CPU state. Now I understand here what I did here. Like I executed the same program from two different terminals. Fine. And now let me see it here via top. Now, do you think that CPU is going beyond 100%? Can you see here like 99.3, like 98.7, 97.7? It is going beyond 100%. And just we say like utilization would be 100%, but definitely that means there are different cores. It is not meaning that CPU is having approximately or utilized 200%. No, it is shared. That means one process runs, time slice ends, it goes back to ready state. You can check the states like in between, like small amount of time, probably you may not realize. It goes back, come back, goes back, come back, ready, it goes back to ready, another process runs. And this switching is happening in milliseconds. And that's invisible waiting queue, which is there in background, is the ready state. Linux does not show the ready state separately, please understand. Processes that are ready and are in run queue are shown to us here. And this is what you see here, R. This R is running state. So when your scheduler selects a process and gives CPU, it enters running state. The example that I was giving you before a while with respect to the police, the traffic police having a whistle who was controlling the flow. Actually, it was a scheduler. Correct? So if 10 process want CPU and only one core is available, how many of them would be running? They would be getting, there would be running only one process. Remaining 9 will remain as ready. Correct? Now let us talk about waiting or block state. And so let me terminate this code. You will realize it is removed from memory. One of the process got removed from memory. Let me terminate this too. You will see that other one is also removed from memory. Now let us address most interesting part here. Now we said a process enters into waiting state if it is expecting some input from you. If it is reading from file, if it is waiting for network, it may give call to sleep function. It may wait for some signal to be given. Now, how will you decide to cross the road? If we take the same example, either the police would be indicating you, hey, you are waiting for something to happen. Till that time, you are waiting or blocked. Correct. So let us try to prove this. What exactly is happening? Let me write one more code. We go back to Emacs. Let us write another simple code. Hash include stdio.h int main. Let me write index. Printf say enter a number slash n double quotes. Sorry, slash n double quotes. Scanf %d ampersand let us print the same. Third, send D slash n x semicolon return 0 bracket. So let us save this code. Correct, and let us compile with assumption there are no errors. Correct. Now after compilation, let us execute this. So I will use again the name for it so that you'll be able to see that. I kept this terminal open. Fine. Let me run. Let me see the top. Let me find top. Okay, can you see our program name there? CPU state 0. So let me maximize this. Can you see my program name there? Yes, no? It would be difficult to see here because it is not found. It is just showing just some processes to us. So now how can we check it for us for the code? Let me first write this EJH. Okay, get the PID of your executable. So our executable name is, PID is 9098. Let me write this PS dash O. Okay, your let us display PID. Let us display state. Let us display command. Here. Okay. Now you will realize for our process it is not shown because we haven't written this for all. Let me write AUX. Correct. Now this case in PID state command. Let us show or let us see it for our code. Grep CPU state underscore 01. Now let us understand what it is showing. It is showing S. Now if you see another terminal, like we executed our code, but it is waiting for something. Now here, like the state shown to us for our code was S. We will understand what exactly that plus means. S means sleeping. Sleeping in Linux means waiting. Your process is not running. It is not ready. It is waiting for keyboard input. So what happened here when exactly you wrote dot slash dot out and when you wrote dot slash CPU state CPU underscore state underscore 01, our program started as a process. So process was created new. Then it was in a queue to be getting executed on CPU. So it became ready. Then CPU was allocated. It was running. And then it was waiting because it is expecting some input. Suppose if I write here number, you will realize the process is gone. Our process is not seen, which was S plus. Why? And the program got the input, it executed and terminated. So it was running, correct? Then it was waiting. Then again, when it was served with the input, process again started running and then terminated. So that is the real state transition happening inside the CPU. You saw that because it was therefore with this S and plus. Fine. Now, why hasn't it showed us terminated state or ended state? Like if I talk about man PS and if I go below and see the states, correct? So we saw R, correct, which was running or runnable. Then we talked about capital S, uninterruptible sleep, waiting for an IO event to complete. And with S, we saw plus. Plus is in the foreground process. Now let us say, like what you write generally. If I type say CPU state dot 01, it is executing and you simply press Control Z. Correct. Now if I try to see the same thing for my process, what is shown there for our file or for our process? Earlier, when we were executing the code, because you must have seen while you work with Linux terminal, most of the times you keep pressing Control Z, Control Z. So now the process state when it should have been S plus. Okay. So let me go back and maybe recreate the scenario for you. Control C. Now let me execute this process. Let me write here PS. We will realize that that process is not shown here. Correct? Because there is no such process available. Because of grep only it is showing us this. Fine. So let me execute this code. Now you will realize what is the state of that process. It is S plus sleeping and it is waiting for some IO to get completed. Correct. Now simply what you did here, you pressed Control Z. Okay. Now what it is showing us, check the state. The process state became T, which was earlier S plus. Correct. Now what exactly happened here? Let us check again the state code. Let us try to understand what exactly that T means, capital T means. We'll understand that S plus plus as well, but let us say T, capital T. It was stopped by a job control signal. So when you press Control Z, actually it is a job control signal. Okay. Now when we talked about that S plus, plus was is in the foreground process because it was executing and it was waiting for an IO event to complete. That's why it was S plus. For other, like for our process, when we terminated it with the job, stopped it by a job control signal, like pressing Control Z, ultimately it showed us the process state to be capital T. Now let us try to see one more process state as Zombie Z. So if I write man PS, though once we saw it, but we'll try to understand it again in greater detail. So it is called as a defunct. So some process states we may not be able to show, but I will try to cover as much as I can. Okay, so let us write again, go back to our code. I hope you must have understood now R, S, and T. Please understand, new and new and ready are not shown to you directly there, but remaining other process states can be visualized or can be seen. Okay, let us try writing now a simple code using system called like fork. And so let me go back to max CPU state 02.c. Dash include. I hope you are following me. Dash include. std dot h dash include sys. And okay, we'll try to edit for a while. Int main. So like when we give call to fork, ultimately we do store the PID. Okay, so let us say we will give call to fork here. If PID equal to 0. What exactly this means? Where are we executing the code? Yes. And in parent, we will ask it to sleep for a while. So you may recall we use this sleep to understand returns and then return 0. Fine. Now let us compile this code. GCC CPU state 02.c dash m32. I'm taking it out only right now. Now you may see, like for example, if I go back and check here, right here, UX, EJH will write so that you can see, okay, you may see here. The PIDs are 10014 and 10015. So if I write PS dash EJ capital H grep dot out, then you should be able to. Oh, so the sleep is done. That's why. And let us go back and check here the PIDs. So PIDs for our code, because we wrote a small number, probably it is completing or terminating that execution. So we'll try to increase that one. Yeah. Now let us see this. If I write this and if I write ps-ux, we'll increase that count so that one can check the status. So here I added 20, so I will keep it as 60 so that it can be bigger. So let me compile, let me execute. Let me do the same thing. ps dash ejs grep.out. You can see 280 and 281 are the processes. So if you see 280, this is 280, which is S plus, correct, and A dot out like 281, which is Z plus, correct. So if I check with top two, okay, it would not be shown because only running or with S are shown, which are waiting for some input or output. Otherwise, everything is everything is not shown here. You can see other states too, like D, I, and so on here. Like if I go back and check this, sorry, check this one again, your dot out is still in memory, correct. So once this termination happens, probably we'll check again AUX. You can see the processor S plus and Z plus. Now once code got terminated from here, from on the other terminal, that dot out was removed. And that's Z actually, if we see, is zombie. Defunct or terminated by. So this is defunct. Fine. Okay. So like here, what is happening? Child finished execution, but parent did not wait. Correct. it hasn't called wait for the process to be there. So child became zombie because child finished the execution. It has terminated, but its entry is existing in your PCB or process table. And this is like advanced understanding in terms of the states. Okay, let us talk about now. Let us try to see the S state, like which we already saw. Sleep, when you write S, like it is saying as interruptible sleep. So the thing that we saw was with respect to waiting for an event to complete. So it was related to input or output. It could be different as well. Like if you use sleep just in your code, that's what like our a dot out was shown. One of the a dot out was shown as Z plus, other one was shown as S plus. Okay, that sleep forces the process to wait or enter into waiting state. Correct. Now, if we consider the similar kind of example, when we executed the code, process creation was done through fork. Okay, what are the code that we executed before a while? Okay, this one, when we executed this dot slash dot out. Correct. Process created, it was waiting for CPU. It was executing your printf, like I am child what executed and now exiting. Correct. And like if there is scanf, then it would be waiting for your input. So once input arrives, probably in this case, we haven't used any scanf. Okay, so let us do that. If I add scanf over there, now whatever was shown as say Z plus, before Z plus, what is there? Let us see. %d, ampersand a, right? Integer a. Yeah, let us compile. Let us execute. Now, if I go here and check the process states now, ps dash aux. Let us try to understand that a dot out. Both of them are S plus now, correct? Because my child probably is waiting here, correct? So if I write say 3, this S plus became Z plus, correct? The other process was remain there because it was having 80 as sleep point. Now what happens? Suppose we don't give input at all. The parent also can terminate its execution, correct? Because we gave 80, so it was waiting for it. And the process state for child was Z plus. You can check it. S plus Z plus is shown there. See this one. Oh, both of them are gone. Now let us say, suppose we execute this and we don't give input at all. Right. So let me just type grep a dot out. Let us check this just. Correct. Now you'll realize, like if I don't give input to 10597. Okay, sorry, 10598 because it was a child. So in between, if suppose parent crosses its sleep time, that 80, parent will leave. We'll see like when 597 is gone. We are not giving any input there to the other side. You will realize once parent goes off, you will never see Z plus state for 598. After the 80 seconds are gone. Whatever we wrote with sleep. Now you can see our process, which was 597, terminated it. Like you go to this terminal. Is it waiting for our input now? You can see there is a cursor. This cursor, we are not sure whether it is for bash or whether it is for your input scanf statement. And that's why like earlier, whatever was S plus, now it is showing it as S. that plus is removed because it became now the background process. We don't know whether it is really a foreground or not. Right now it is background in background. If it could have been waiting for my input, that could have been the one can say plus sign over there with respect to my process. Like for example, this 598. Okay? Now if I give say 7, now I haven't pressed any enter key there. Just press 7. It got terminated. Now whatever is shown here is actually the shell prompt. So if I write ls, then I can see that ls command output is shown. And this is happening in Ubuntu kernel. Okay. So this is what like how exactly you see these process states. Just it is not good to really understand it as a say one can say like a, just only as man pages, but ultimately it is where exactly you are trying to understand how the process states are seen. Fine. Okay. Now how exactly this is decided that the states or the processes to be executed. Okay. I hope you understood. If you have any queries, please ask me. Yes. Any queries, questions? No? Okay. So let me show you with respect to say some other cases. How can I see the process states? Now let me go back and write man ps. Okay, let me go back again to the states or state codes. Let us understand D, uninterruptible sleep. It is waiting for IO operation that cannot be interrupted. And that's what it says, uninterruptible sleep. For example, when a process waits for disk IO, we can do this by simulating something like that, like a heavy read, heavy disk read, definitely. Now, if at all it is to be done, how exactly we can do this? Okay, we'll try to understand it through some example. Please note, what are the process which enters into D state, it cannot be killed very easily. So if you are trying to display a very big file, it will take some amount of time. Okay, so let me do it. Let me try one thing. Let me write PSQL. I'm making use of PSQL here to introduce this thing. Create table. Okay, let me see how many tables are. Create table. Say X1, 2, 3. I hope it is not there. 5, 6. Integer. Insert into X1, 3, 4, 5, 6. Values 10, 20. Insert into X1, 2, 3, 4, 5, 6. Select star from. So I'm reading and inserting into the same table, reading from the same table, inserting into same table. So it looks very fast, correct? Let us try to understand here. Yes, correct. So if I write ps dash a, try to see wherever it is pts 0. bts slash c. Yeah. So you can see, okay, the things there. You can see, yeah, good. So, like you may recall, we executed this and we asked by press Control Z. It is still there, right? You can see it is T. Now we are more interested into this PSQL command. Let's see this one. Okay, which one? This one. Okay, it is S plus. It is waiting for our input. Let me execute this. It looks very fast, correct? Now you will realize that it is taking some amount of time. Okay, it got executed. Let me fire this again. Okay, it is waiting, correct? It is still showing us S plus. Can you see S plus always there? USR lib usko, try to concentrate on this one, correct? 10727. It is not showing us for other cases that it is changing the state. Now let me go and do the same thing again. It will always show me that it is S plus because it is working on it. Correct? Complete control was given to my code. Okay, which is PSQL. It never changes the state. It remains S plus. For PSQL client. Now what happens suppose if I press Control Z? Okay, if I did this and if I press Control Z, fine, let me check it now. Now you will realize the process suddenly entered into an because you press T, Control Z, ultimately it entered into terminate, stopped by the user signal. But is it not working internally? Correct. Like a number of records that are executed are definitely more than it is still executing that command. You could have seen probably like the data insertion could have been completed. It again back to S plus, and this is the transition between the states. Correct. Once you see like it is done with it, you should see Nitin equal to hash as a prompt. Right? Once it does it. Right? It is PSQL and then UX S plus S plus S plus S plus. You can see what happened. Sorry, what happened was on the terminal. You could see this Nitin equal to hash was shown the prompt. But then question is like what exactly it is trying to do? What is exactly it is trying to add? It is trying to insert those many records, the number that you see here. It is actually doubling these. If I want to read that number, ultimately it is like 1 crore 25 lakhs 82,912. This is very big, correct? So if I'm trying to enter those many records in the database file, what exactly it did between that time? It was trying to insert. Your complete processor was behind that. Now let us try to understand the similar kind of stuff rather. What happens when we try to write onto the say pen drive, like if it is ISO file, you must have seen while you try to copy or install any operating system onto other device, like most of the times the images created are ISO. If you are creating a disk image, same to same copy. So for that purpose, let us understand one command. Okay. So what we seen here with respect to this PSQL example, though it is writing, but CPU was given completely to it, and that's why it was always showing us until unless we send it to background through the terminal like signal. But by that time it is showing us S plus. You can see now it is gone. It is not there. Correct? So probably let me terminate that other two, the CPU state. You will realize now that T also is gone. Now you will see with bash, it is small s, capital S, plus. Now, what is this small s means to us? With plus, we saw it is foreground activity, waiting for some IO kind of stuff. Let us understand that smallest. Smallest ultimately is the session leader. Under it, majority of the processes are getting executed on that terminal, because here the parent was bash, and that's the reason why it became a session leader. Correct? This became a session leader for that whole process tree. Now let me use a command. Let us say dd. It converts and copy a file. So it is a Unix utility used to copy and converting the raw data. Like it is not like CP. CP does what? Copies files normally, but DD works at lower level and copy the data block by block. Fine. So this is often used mostly by for creating disk images or generating large test files. So let us try to understand with this how exactly one can see that D. Okay. So let me try writing this. Please note down these commands like while I'm writing. Anyway, I'm going to make this available. Probably. I hope I started recording. Yeah, I started recording, so you definitely can see this. So dd. Let me write if equal to save slash sorry. Okay, so I have written this command. Now what I stated about dd? Okay, dd is meant for we want to create a file. Okay, which is not simply as copy command. Now, what exactly the other things mean here for us? Fine. So let us understand. So first I wrote if equal to slash dev slash 0. If means input file, if. My file input file is slash dev slash 0. Now what is slash dev slash 0? In Linux, slash dev contains a special device files, and slash dev slash 0 is a special virtual device that produces infinite 0 bytes. Okay, so if you read from it, it will keep giving you 0000. It never ends. It is not a real file on the disk. It is generated by the kernel. So we are reading zeros continuously from the kernel. That's what it means. Then we wrote space OF equal to big file. OF means output file. So all the zeros we read from slash dev slash 0 are written into a file named big file. And if the file does not exist, like we haven't created in this current working directory CA552, this file, so it will be automatically created. So if it is existing, then it will overwrite. Then we have BS equal to 1M. Here BS means block size. Each block should be of 1 megabyte. That's what we are writing, 1 MB, 1 megabyte. So instead of copying byte by byte, DD copies it in chunks of 1 MB at a time, which helps us improving the speed. And then we are saying count equal to 2000. This tells DD how many blocks to copy. So since the block size is 1 MB and count is 2000, so total data would be what? Total blocks are 2000 count. Okay, each block is having 1 MB size. That means 2000 MB. That means approximately 2 GB. It is not exactly 2 GB, but approximately 2 GB. So this command creates a 2 GB file filled with zeros. So let me execute this. Let us go here and check. Can we see D plus? Yes. So this D, what exactly this D means for us? Like you can check because it is creating a 2 TB file. So it would be taking, sorry, 2 GB file. It would be taking definitely some amount of time. So gone because our file got created. So if I write ls-l tr, you can see this file was created. Big file. What is the command that I applied? I'm adding this command for your reference. Okay, into chat window. Please note down this. Can you see the command in chat window? You must have got it. Correct. So what we did was we created that file. Fine. Using DD, and we could see that the state became the file. Now let me do this. Cat big file. I can do like I can read this. Okay. This big file to the device. Slash dev slash null. So it is trying to read it. Correct. Into the device. Okay, let us go and check. So it will take some time. For example, D plus, you can see for cat command, it is showing us D plus. Okay, now as the file reading was done, right? It removed it. So sometimes you may see state D, capital D, sometimes plus. So D state when cannot kill very easily. Okay, please understand. This is serious kernel level waiting, and that is advanced understanding that you are having now. I hope you understood this D. So let us check what exactly that D was one more time. Let us understand that. So when I have fired a command and I explained what exactly the command means to us. So D is uninterruptible sleep. Usually IO because it was reading zeros in terms of number of blocks of 1 MB each, and total number of blocks created were 2000. So approximately we created a 2 GB file. Now let us try to understand capital T. So for few others states rather, I would not be showing them. I already showed you D, R, S. Okay, even we saw T. Fine. So like sometimes we also saw that Z too. Correct, for other processes. So like we saw R, we saw D, we saw S, we saw T, capital T rather. Then we saw Z. Please note this X, you can see the text written there, dead. It cannot be seen. It is never shown to you. Fine. Why? Because internally kernel has that dead state. You will never see this. neither me nor you. But internally, after termination and cleanup, process is fully removed. Correct? And that's how the things are seen by us, like process states. Some states, like say for example, I will see when we do address threading, or even W with respect to some other aspects. Right? So I hope you understood what I was trying to communicate today. Okay, with respect to the process states. So if you have any questions, please raise your hands and you can ask me the questions if at all they are there. I'm stopping this recording.